Presenters, ladies and gentlemen, welcome to the parallel technical session of Icpeam 2020. I'm very excited to welcome you all to our session today. My name is Bawadi bin Abdullah from University Technology Petronas. As a chairperson for today's session, the theme of our parallel technical session today is Green and Advanced Material Engineering. We are very fortunate. We have 7 sessions that will go parallel. For reminder for all the audience, for any inquiries related to the topic being presented, you may type your questions in the live Q&A or discussion forum. Just click either one of the icons at the bottom of your screen and type the question in the checkbox that appeared. The presenter will answer your questions after he or she completed the presentations. We're going to have a welcoming remark from Chair of Chemical Engineering, Associate Professor IR Abdul Halim Shah, and will be...
Good afternoon, ladies and gentlemen. On behalf of the organizing committee, I wish to extend a warm welcome to you for attending the International Conference on Process Engineering and Advanced Materials 2020, which is well known as Icpeam 2020. This is the 6th conference in a series that began in 2010 under the World Engineering Science and Technology Congress umbrella. Icpeam 2020 is a chemical engineering-based conference with the theme Sustainable Future, the Inevitable Change. Our goal is to spark a broader discussion on the opportunities and challenges of the current technological innovation, including the Industrial Revolution 4.0, in achieving a sustainable future. I believe that Icpeam 2020 is the ideal platform for scientists, engineers, industrial experts, academicians, and scholars to disseminate the most recent findings in their respective field. The conference also provides excellent opportunities for the participants to exchange new ideas and experience, as well as to establish research and business relationships with global partners in preparation for future research collaboration. This year's conference has attracted over 100 participants. Our technical program features 5 tracks, which include Green and Advanced Material Engineering, Sustainable Process Development, Process System Engineering and Optimization, Advanced Kinetics and Thermodynamics Engineering, as well as in industrial tracks. Furthermore, the organizing committee has invited 3 distinguished plenary speakers to share their experience and knowledge. I would like to extend a warm welcome to our plenary speakers, Datuk Muhammad Arif Mahmud, Professor Junji Inukai, and Professor Chris Aldrich, who represent leading experts from the industrial and academia. I sincerely believe that this conference exchange of ideas will help to establish new connection, create collaboration, and cultivate friendship between academia and industry. Last but not least, I would like to express my gratitude to our co-organizers, participants, reviewers, sponsors, and organizing committee for their significant contribution to the conference success. I wish you a successful and a rewarding experience at Icpeam 2020. Thank you.
Okay, without any further ado, let's put our intention together and to our first presenter. So she's Nur Fahana Ajwa Mustafa from University Technology Petronas. Her title for her presentation today is Effect of CO2 Concentration in the Gas Feed of Carbon Dioxide Absorption Performance using aqueous potassium carbonate promoted with glycine. Without further ado, please welcome Nur Fahana Ajwa Mustafa.
Assalamualaikum. I am Nur Fahna Ajwa Mustafa from Chemical Engineering Department, University Technology Petronas. I will present my paper entitled The Effect of CO2 Concentration in a Gas Feed on CO2 Absorption Performance using aqueous potassium carbonate promoted with glycine. Along my presentation, I will explain on the introduction, methodology, results, and conclusion. Natural gas is an important fuel since it is widely used in the transportation, ammonia production, syngas production for domestic use, and the electric generation. Due to this scenario, natural gas has an increasing demand globally. The possible solution of this issue is to explore the high CO2 content of natural gas reserve. The challenge to explore this high CO2 content reserve is to develop an effective process for bulk CO2 removal from natural gas at offshore conditions. This is because the bulk CO2 removal will cause the corrosion to the pipeline. So, there is the challenge to develop an effective process for the high CO2 concentration removal. There are four technologies that is well established, which are the adsorption, membrane technology, cryogenic distillation, and the absorption. In this project, we are focusing in absorption technology since the absorption is the most matured technology as compared to the others. In absorption system, the commercial solvent that currently used is the amine-based solvent. However, amine-based solvent poses several drawbacks, which are the high volatility, high corrosivity and toxicity, has thermal and oxidative degradation, and require higher regeneration energy. In this project, we are using the alternative solvent, which is the potassium carbonate with glycines. Potassium carbonate itself is non-volatile, less corrosive, no thermal degradation, it requires heat of absorption, and it has lower cost as compared to the alkyl amine. In this project, we were using the packed bed absorption, bench scale packed bed absorption equipment. So this is the equipment. The gas will be mixed in the CO2 mass flow controller and will be mixed and compressed into high pressure vessel and compressed into the bottom of the column, while the liquid will be pumped using the high pressure liquid pump that equipped with the back pressure regulator to the top of the column. This will create the countercurrent flow between the gas and the liquid phase. The absorption will be allowed to running until the system has reached the steady state conditions. Once the system has reached the steady state condition, the CO2 concentration will be analyzed using the IR analyzer for each sampling point along the column. In this project, the operating parameter that has been used is 40 bar, 60 degrees C of solvent temperature, 15 to 30 mole percent of CO2 inlet concentration, 1.5 kilogram per hour of gas flow rate, and 0.2 liter per minute of liquid flow rate. This is the CO2 removal efficiency formula, which is CO2 mole fraction at the outlet minus CO2 mole fraction at the inlet divided by CO2 mole fraction at the inlet times hundreds. This is the result of this paper. As we can see from figure 1, lower CO2 removal was acquired as the CO2 concentration in natural gas increased. Higher CO2 concentration will increase the total CO2 mole in natural gas, where it will resultantly reduce the L over G ratio. As L over G ratio reduce, there is less contact between liquid and the gas phase. Therefore, lower CO2 removal will be acquired at a higher CO2 concentration. As from figure 2, we can see that the CO2 removal efficiency decrease over increasing CO2 inlet concentration. At constant pressure, an increase of the CO2 inlet concentration will be will increase its CO2 partial pressure. However, in this case, the CO2 partial pressure effect is not significant. It's just about 1.2 megapascal. So the main cause of this behavior, the reduction of the CO2 removal efficiency over increasing CO2 inlet concentration, is due to the limited reactant of liquid phase to absorb the CO2 concentration in the natural gas. The conclusion of this study, we can see that decreasing trend of CO2 removal efficiency from 79.24 mole percent to 65.79 mole percent as CO2 feed concentration increase. This study also demonstrated that the efficient absorption, which can absorb up to 79.24% of CO2 from natural gas using potassium carbonate promoted with glycine. With that, I end my presentation with thank you.
Okay, let's see if we have any questions from the live Q&A and also a discussion forum. Okay, so far none. But I have maybe one question for you, Nur Fahana. Okay, your topic related to CO2 concentrations. So what do you think in the, because we're talking about greenhouse gases, CO2 one of them. So what do you think will be in terms of the technology in the future, in terms of absorption or consequences of CO2?
Uh, Due to the higher concentration of CO2 in the reservoir, so we need currently I'm doing my research regarding on the new technology instead of the pack bed column. It's apply the same method like the pack bed absorption column, but it has the energizer to enhance the mass transfer between gas and the liquid. So it's apply the same method like the pack bed absorption that I used to study before. But this technology applies the energizer to enhance the mass transfer. It's the same mechanism, but it's smaller system. Our problems now is on the footprint. The if you install the pack bed at the offshore, so the footprint will be large, so it will consume more footprint and the load on the platform. So currently we are working to reduce the footprint of the reactor in order to absorb the CO2 directly from the platform.
Okay, thank you, Nur Fahana. I guess no more questions from the audience. Thank you very much.
So,
Okay, next, our presenter, she's coming from Sojo University, Japan. Okay, the title for her presentation today is Layered Double Hydroxide Supported Cobalt Nanocluster Size and Effect in Catalytic Hydrogen Generations. Without further ado, please welcome Aisha Mahfouz from Sojo University.
Hello and welcome everyone. My name is Aisha Mahfouz. I'm a postgraduate student from Sojo University. And today, on behalf of the authors of this paper, I will be presenting our work regarding layered double hydroxide supported cobalt nanocluster, controlling particle size and effect in catalytic hydrogen generation from sodium borohydride hydrolysis. So particle size is an important parameter that determines the catalytic activity of metal nanocluster. In particular, previous research have shown that catalytic activity improves significantly when particle size is less than 5 nanometer. For example, a landmark research done by Haruta and co-worker in 1993 have shown that the catalytic activity of a supported gold particle increases with a decrease in particle size when it is used as a catalyst in carbon monoxide oxidation reaction. This is because compared to the larger particles, small nanocluster has a larger specific surface area as well as high surface energy, contributing to the high catalytic activity. However, because of the high surface energy, small nanoparticles are usually unstable and they tend to agglomerate, forming a larger cluster, making the synthesis difficult. Because of this, a usage of a suitable catalyst support, such as LDH, is beneficial. Such material prevents metal particle from aggregating and allows the growth of particle to be controlled. Solid double hydroxide or LDH is a class of two-dimensional layered anionic compound. Its basic structure is similar to boosted octahedra, in which one metal center is surrounded by 6 molecules of hydroxide. This H-sharing octahedra creates an infinite hydroxide layer, and for LDH, some of the divalent metal are substituted with a trivalent metal, creating this positively charged layer. To compensate the excess charge, there is an ion occupying the interlamellar space. Common types of divalent metal in the hydroxide layers are cobalt, magnesium, and nickel, while common trivalent metals are aluminum, chromium, and also iron. As for the anion, common types of anions are carbonate, nitrate, and also chloride. So because of this unique layered structure, as well as its exchangeable interlayered anion, LDH is a suitable support material to be used for catalyst support. So the objective of this research is to control the size of cobalt nanocluster, and this is done by varying the concentration of cobalt citrate in the ion exchange step. And secondly is to evaluate the effect of cobalt nanocluster size on its catalytic activity, and this is evaluated from the hydrogen generation from sodium borohydride hydrolysis. For the preparation of cobalt nanocluster integrated on LDH, the catalysts in this experiment are prepared using three steps. It starts with the synthesis of a nitrate type of magnesium aluminum LDH, where nitrate is the main interlayer anion. Following that is integration of cobalt citrate, whereby the nitrate anion is replaced with cobalt citrate in ion exchange. And thirdly is the chemical reduction with sodium borohydride, whereby the cobalt citrate in the interlayer is reduced with sodium borohydride aqueous solution to form cobalt nanocluster. So I will explain in detail for each step. For the synthesis of the nitrate type of magnesium aluminum LDH, in a typical procedure, a mixed metal salt containing magnesium and aluminum nitrate of molar ratio 2.1 is added dropwise into a solution containing sodium nitrate, and at the same time, sodium hydroxide at 2 mol per liter is added to maintain the pH at 10. Throughout the dropwise addition of magnesium and also aluminum nitrate, the solution is vigorously stirred at 55 degrees Celsius. It is then filtered and rinsed and dried at 100 degrees Celsius. And I refer to the sample as nitrate LDH for simplification. For the intercalation of cobalt citrate, an equimolar ratio of cobalt nitrate and also citric acid is added with 300 ml of water. Then sodium hydroxide is added and increase the pH to 10 before the 1 gram of powdered nitrate is added. This whole solution is stirred for 12 hours at 50 degrees Celsius, is then filtered and rinsed. Half of it is dried at 60 degrees Celsius, and I refer to this sample as X millimolar cobalt citrate LDH, where X refers to the various concentration of cobalt citrate solution used for preparing the sample, that is 4, 2, 1, and 0.5 millimolar. And half of the others solid collected is used in the reduction step. So for the chemical reduction with sodium borohydride, 5 grams of sodium borohydride is added with 50 ml of water. Then the wet X millimolar cobalt citrate LDH is added. This whole solution is stirred for 2 hours at 50 degrees Celsius. It is then filtered and rinsed and dried at 100 degrees Celsius. And I refer to the sample as X millimolar cobalt LDH, whereby X refer to 4, 2, 1, and 0.5 millimolar cobalt citrate solution. So this is the X-ray diffraction pattern of the set of samples synthesized from 0.5, 1, 2, and 4 millimolar cobalt citrate solution. This refers to the X-ray diffraction pattern refers to the nitrate LDH, and the red line refers to the XRD after anion exchange, and the blue line represents the diffraction pattern of the sample after reduction with sodium borohydrate. So in all these four samples, a similar turn of shift in the basal peak 003 can be observed. For example, here in all four samples, you can see that the peak 003 after ion exchange shift to the left, and after reduction in sodium borohydrate, the peak 002 shift back to a higher to theta angle. So because the trend is the same for all samples, I will focus on one, which is the 0.5 millimolar cobalt LDH. For the nitrate LDH, the calculated basal spacing is 0.88 nanometer. After ion exchange, the basal spacing increased to 1.24 nanometer, which indicates a successful intercalation because the basal spacing expand to accommodate the larger size of cobalt citrate ion. Following that, after reduction, the basal spacing obtained here is 0.79, and this actually represents the basal spacing occupied with the carbonate anion. So on all four samples, there are no peak related to cobalt phase appeared in the reduced cobalt LDH because of the particle size that are irregular. In this slide, it shows the effect of cobalt citrate concentration used in the ion exchange on the cobalt cluster size. Here is the time images of all four samples, 0.5, 1, 2, and 4 millimolar. The yellow ring here highlights the cobalt particles that is identified using EDS. And from each images, we can see that the size of cobalt nanocluster obtained, you can see that the size increases increases when the concentration of cobalt citrate increases. And based on the average cobalt nanocluster diameter versus the concentration of cobalt citrate, the plot of the graph indicates that the average cobalt nanocluster diameter increases with the concentration of cobalt citrate. So the catalytic activity is evaluated from sodium borohydrate hydrolysis. So sodium borohydrate is basically an energy-dense hydrogen storage material, and it reacts with 2 mole of water, producing a pure humidified water that can be delivered to portable devices for energy. In this research, the volume of hydrogen is measured using a method called water displacement method, whereby in a reactor contains 98% of water and 5% of sodium borohydrate and also sodium hydroxide. To initiate the reaction, 50 milligram of catalyst is added. Once it is initiated, hydrogen is generated, and the volume of water is evaluated from, the volume of hydrogen is evaluated from the volume of water. So the results obtained for all four catalysts is shown here. From the graph, it shows that the volume of hydrogen generated over time for all four samples. As you can see here, the hydrogen generated increases with the increase in cobalt nanocluster, with the increase in concentration of cobalt citrate solution. Essentially here, this is the graph that shows the average the hydrogen generation rate against the average particle diameter of cobalt nanocluster. So you can see here the hydrogen generation rate increases with the increase in particle size. And this can be explained by the accessibility of the active cobalt species in the interlayer of LDH. Compared to the bigger particles, smaller cobalt nanocluster has a limited access of the borate ion with the active cobalt surface because of smaller interlamellar space. However, the bigger particle has a larger interlamellar space, which has easy access for the bore ion to reach the surface of the active catalyst. So as a conclusion, size of the cobalt nanocluster supported on LDH can be increased by increasing the concentration of cobalt citrate in the ion exchange step. And secondly, for LDH supported cobalt cluster, catalytic activity increases with cobalt cluster size. And is mainly limited because of the accessibility, as well as probably there is an optimum cobalt nanocluster size that is necessary for maximum efficiency. Thank you.
Okay, let's see whether we have a question from the audience or not. Okay, all right. I have a question for you, Aisha. So, how you do, how you control the sizing of nano cluster in your research? How you do that?
Okay.
Because very hard to control the size.
Okay, basically, from my experiment, we control the size of cobalt nanocluster by changing the concentration of the cobalt citrate precursor as a metal precursor for the metal particle. So basically, if you increase the concentration of cobalt citrate solution, the end result of the cobalt nanocluster increases. So this is based on this is because of the advantage of the layered structure of LDH that allows the control or the confinement of the cobalt citrate in the interlayer, and which at the end controls the size or limits the size of the cobalt nanocluster in the end product.
Okay. Uh, do you think that there will be other application for your catalyst beside hydrogen productions, or
Uh,
what do you think?
Yes, as metallic cobalt itself is an active catalyst for various application. One example that I can think of right now is in terms of environmental protection. For basically, cobalt can be used as a catalyst to be used as to reduce pollutants. For example, penitrophenol into 4-aminophenol. So that's one example where this cobalt particle can be used. And maybe this is another example of where this catalyst can also be used.
Okay, good. Thank you very much for the presentation and Q&A session.
Thank you very much.
All right. So next presenter will be coming from University Technology Petronas, Dr. Muhammad Ayub. His title for today is Synthesis and Characterization of Waste Eggshell-Based Moryllinite Clay Catalyst for Biodiesel Production from Waste Cooking Oil. Without further ado, please welcome Dr. Ayub from UTP.
Very good morning. I'm Dr. Mohammad Ayub from ICU CBBR Institute of Self-Sustainable Building, Ministry of Technology, Petronas, Malaysia. Today my topic for talk is about synthesis and characterization of waste eggshell-based monolite clay catalyst for biodiesel production from waste cooking oil. First of all, we will introduce what need required for biodiesel for future. You know very well about that one, that for future green fuel is important because fossil fuel is going to reduce day by day, and for future we need alternative fuel. That biodiesel is one of them, and it is already well known that biodiesel properties are close to that pet biodiesel. So we can say that biodiesel is exactly same as petrol diesel that is already available and that is coming from fossil fuel. So alternative fuel, green fuel, that is biodiesel, is our future energy. Therefore, we are concentrate on that one. As you see that properties of biodiesel according to ASTM D675 is exactly match with that our fossil fuel diesel. Okay, so if we come from that, where we can get that biodiesel, different resources available. Edible oil is there, like sunflower, rapeseed oil, cooking oil, soybean oil, non-edible oils, because when edible oil is creating crisis for food, then we will looking for non-edible oil that is often called second generation. So in that one, we are checking which is not crop for food. Sometimes we are using chetrofa oil, neem oil, or castor. That is not direct our food. And other alternative is waste oil. What we are using for our purpose, utilize that oil, and then it is going to waste. We collect that one, and we can again produce biodiesel from that one. So today our topic is also from waste cooking oil. So we can easily collect that waste cooking oil from homes, because as you know very well, at home we are frying thing 1 2 3 times, and then after that, when oil is going to black, it can be going through it, because it cannot feasible for cooking. So that is waste cooking oil. So basically that is potential for production of biodiesel, because they have free fatty acid we can convert in the form of triglyceride, that is FAME, and we can utilize for future different work done on that type of waste cooking oil, with different catalysts available, like CaO, kaolin clay, H2SO4, homogeneous, heterogeneous type catalyst, different reaction condition available to produce that one. We get maximum 100%, 90%, but with different conditions. There is some limitation for each process with different type of catalyst. You can see 2011 to 2020, there is number of researchers already work on that one, but still there is a gap that what type of catalyst we are using and what type of feedstock we are using for biodiesel production. If we see, we are using basically catalyst that is coming from the eggshell, because eggshell is also waste. We are using waste cooking oil, and eggshell is other waste. Two waste combined to get biodiesel. That it's mean that we are going to economize the process of biodiesel production. So in methodology, you can see that we have clay, that because clay is our support for that eggshell based catalyst. So we are using marmolite clay, that is calcined at 800. Then what we have to do, we mix it with that proper way, and we mix it with KOH, that is to make it alkaline. And other way we can use dehydrate and characterize it is simple alkaline based monomolite clay. And another way we can also use eggshell base, that is also used for CaO purpose. So we can add physically, and we can mix, and we can utilize for that one. After preparation of catalysts, we have different characterization like FTIR, XRF, FSM, and BET surface area we have done. And then after that, we have checked the biodiesel production via our process GCMS. We have different parameters which are utilized for that purpose. Temperature 60 times 30 to 60 minutes. Ratio is 112, and catalyst loading is 28%. That already standardized with our previous work, because our group is working on biodiesel last 5 years. So we have already fixed that parameter at different catalysts. So the same parameter we are using for that purpose. So we find some result we can share here, that when we mix chicken eggshell with clay, we have elemental analysis. We check that mostly calcium is utilized with the help of that one. We also check some other type of eggshell, like quail eggshell with clay. So yeah, we can see that properties is very close, not too much difference with the chicken and quail. Just slight difference is there, that is not too much. So we can say that we can take any type of eggshell combined with clay to get our final product in the form of catalyst. So we also have done properties of physical properties of catalyst for BT surface area. You can see that chicken and quail have close surface area 9.25, and pore volume and pore diameter. Basicity, you can see that it is very good in the form of basicity. Both have same. Acidity is low, because mostly in the form of calcium. So therefore, more towards basic Hammond test, we can see that it is 10.2 to 10.8. So we can say this our catalyst is basic. In the form of morphology, we can see that same image of produce morphology from activated monomolite clay. First A, you can see there is some morphology is you can see some spaces there, but when we add with our chicken eggshell and quail eggshell, you can see the space is going to fill, and there is some other gaps available there. So it's mean our process you can see slightly dark and white. So after adding that quill shell, we can say the mixing is there, and quill effect of calcium available there from same image. Similarly, if we see that FTIR, we can easily see that FTIR after adding that eggshell with clay is clearly same. There is no effect. It's mean they are compatible with each other. On the other hand, when we see the result about um, biodiesel production with the help of a different method, because we are using different method. On conventional method, we check for both that what happened with chicken marmalade and quail marmalade. We can see that conventional method with 2 weight percent, around about 95 to 90 to 95% same we can get with the help of 2 weight percent. While when we are microwave, in microwave there is one benefit that in conventional 4 to 5 hours required, but for marmalade just 30 minutes. Within 30 minutes the process is getting 50% to 80%. On the other hand, when we are using 5 weight percent of that catalyst, we can see that 100% production of biodiesel is this, because total waste cooking oil convert in the form of fame. So in both case, whether it is chicken or quail, both are same. While in microwave, it is also a good sign that within 30 minutes that chicken is just 60%, but the quail form of that catalyst, they got around about 98% conversion from waste cooking oil to biodiesel. It can easily clear that uh, whether it is chicken or quail, but quail have some extra properties that their calcium and some alkaline content are higher, so it is also compatible. Maybe due to that one, mm, if we see morphology, the cap is slightly higher, maybe reaction is higher inside the catalyst, so therefore more conversion of that waste cooking oil into biodiesel is there. So we can see that both catalysts are working, but quill based monomer clay is more compatible and more biodiesel production is yield is there. So overall, we can say that the appropriate catalyst with the help of egg and coil-based monomer clay is successfully prepared, and different parameters also measured with the help of physical and characterization process. And we can say that that is successfully stable for different values. But one thing important, that quill-based catalyst, quill-based monomer clay catalyst is more feasible, because they provide more than 90% yield of biodiesel production for meat cooking oil. Also, for future, we are working for that, how to make it different parameters changing and other parameter and kinetic check whether it is work for uh, big scale or not. So it is for way forward for future. So overall, our work is done with the help of lab scale. Thank you very much for your concentration, for your work. Thank you very much.
Okay, thank you for the nice presentation, Dr. Ayub. Okay,
Thank you very
I have a
much.
few questions for you here.
Yes, yes, yes. Thank
Okay,
you.
one is from myself. You see
Yes.
that the eggshell basically is very difficult to collect in the huge amount. Okay, so what do you think in the future whether this particular research can be commercialized or not based on the
Yeah,
safety of
thank
the
you very much, Dr. Wadi. It is very important thing, because when we start this project, same thing we are thinking about that one. Availability is very important factor for any research type of things. So because you can see that daily routine in Malaysia and everywhere, we are using too much egg. If we have contacted some restaurant and other, so we can easily get a lot of eggshell from there, and we can collect easily, and it can never be finished, because egg should be continuously available in everywhere. So one thing is important, if we are using a normal eggshell or quail or organic or non-organic, then another factor, because we are tried our best that easily available eggshell we can utilize. That is why we are using eggshell that is easily available. Tesco, Ion, everywhere we can. So in a restaurant, they are mostly using same eggshell we are using.
Okay, thank you, Dr. We have one more question. What type of eggshell that you're using for your research? Is it organic or in non-organic? If there any differences between them in terms of the content?
Thank you very much. This question very good question. Actually, I'm using non-organic because organic eggshell slightly high price, and people are not too much utilized. Again, availability should be problem. But on other hand, when we are talking about its content, obviously organic have more content, like more calcium, more other factors, slightly metals and other, that more helpful. But due to availability, because not too much people are used to organic, therefore we are using which is easily available, and number of abundant not stop over any feedstock, therefore we are using non-organic.
Okay, thank you very much for the response. Very appreciated.
Thank you.
Okay, next, our presenter is from International Islamic University of Malaysia, No Azrini Nadiha Azmi. Her presentation today related to antimicrobial properties of menthol and fatty acid-based deep authentic solvent, the future antibiotic. Without further ado, let's welcome No Azrini Nadiha Azmi.
Assalamualaikum and good day everyone. I am Nur Azrini Nadiha binti Azmi from International Institute for Halal Research and Training in HART, IIUM Malaysia. Will be presenting my research, evaluation of the antimicrobial performance of menthol-based deep solvents as potential future antibiotics. In today's world, drug-resistant infections are a serious threat to people's health. Every year, hundreds of thousands of lives are lost due to infections that no longer can be treated with existing drugs and antibiotics. Several studies have found that bacteria have acquired resistance as a result of extended treatment with conventional antibiotics, making standard antibiotic treatment not as effective as it is before. Thus, discovering new antibiotics is crucial to improve the modern medicine and save the world. Triggered by the strong antimicrobial activities of menthol and various fatty acids, eutectic mixtures based on the components are developed, producing new solvents that have possibilities to become a new antibiotic. In this research, an insight into the antibacterial activity of the deep eutectic solvents formed from menthol and different fatty acids are expected. I mentioned deep eutectic solvents a few times before. What is that? Let me introduce a new improved version of ionic liquid, a mixture of a chemical that acts as hydrogen bond donor and chemical that acts as hydrogen bond acceptor with accurate molar ratio, where reduction of melting point then occur, causing it to become in liquid state at room temperature, preferable over conventional solvents due to the properties. It is easy and simple to prepare. Research has shown that it has low or non-toxicity at all, is cyclable, has cheaper cost, high biodegradability, wide availability of raw materials, and also eco-friendly. What I used in the study is menthol and several fatty acids such as propanoic acid, butanoic acid, and hexanoic acid due to their individual antimicrobial activity. Moving on to the next slide is the methodology part, which is this diffusion test. Among the most versatile methods to measure microbes' resistance against antimicrobial agents. Almost all of the published methods consider any inhibition zone around the filter paper disc to indicate antibiotic activity. The distribution test is divided into 3 days. The first day, to grow the bacteria, prepare the agar, and prepare the sample, positive and negative control. In day 2, we start the distribution assay and we incubate the sample and bacteria together for 16 to 18 hours. The next day, we start to measure the microbial inhibition zone, if any. Next is the results and discussion part. The formation of deep reactive solvents are considered successful if it is in liquid state at room temperature. In the study, out of 6 fatty acids used with menthol at 1:1 molar ratio, 6 of them are successful and 2 is not successful. The successful one is mixture of menthol and propionic, butanoic, hexanoic, octanoic, decanoic, and levulinic acid, which give liquid state at room temperature, while menthol with palmitic and dodecanoic acid at 1:1 molar ratio is not successful and forms solid mixture at room temperature. You can see the example in the figure. For example, menthol and butanoic acid, it gives liquid state, and menthol and dodecanoic acid is solid. This might be because of the menthol and dodecanoic acid is not suitable, or the molar ratio is not appropriate. The second part is thermal analysis of deep reactive solvents. The figure shows the thermal profile of DES4, which is menthol and octanoic acid. You can see that all the peaks are endothermic, suggesting fusion process is occurring. Endothermic process is a thermal event of a material where energy is absorbed by the material, which appears to occur in this case. This is similar to all differential scanning calorimetry analysis of all successful DES in the study. Lastly, the antimicrobial properties evaluation of deep reactive solvents. 3 bacteria has been used in the study, which is 2 positive gram, which are B. subtilis and S. aureus, and E. coli, the negative gram bacteria. From the result, we can see that all DES have antimicrobial activity, but the highest one is DES2, which is butanoic acid and menthol for positive bacteria. For negative gram bacteria, DES3, which is hexanoic acid and menthol, has the largest inhibition zone. How does this DES work as antimicrobial agent? First, we must know that the bacteria can be destroyed through 2 means: bactericidal action or bacteriostatic action, which is to prevent the growth. Firstly, the possible mechanism might be the inhibition of membrane enzymes, which are essential for bacterial growth. Secondly, restriction of bacteria capability to take up nutrients that they need to stay viable. Next is permeability alterations of plasma membrane, where cell metabolites leakage can occur. And lastly, autolysis of bacterial cell walls results from decrease in membrane fluidity. As a conclusion, antimicrobial activity of different DES was assessed against 3 types of microbes, and it can be seen that all DES have antimicrobial activity. DES2, which is menthol and butanoic acid, had the largest inhibition zone against both gram-positive bacteria tested, while DES3, menthol and hexanoic acid, possessed the highest antimicrobial activity against E. coli, which is a gram-negative bacteria. However, a more thorough study on antimicrobial activity of DES should be carried out against wider array of microbes. But it can't be denied that this DES might be one of the components to produce antimicrobial agents in food, cosmetics, or even pharmaceutical area as it consists of natural constituents. That's all from me. Thank you.
Thank you, Azrini, for the presentation. Okay, we have one question for you, Azrini.
Okay, thank you.
Okay, we talk about deep authentic solvent. What is main differences between this type of solvent with ionic liquid?
Um, this one is a new generation of the component that we use is ionic liquid. For example, if in during the dissolved components such as menthol, something like that, is different from.
Hmm. Okay, okay. Thank you very much for the answer. Let's see if we have more questions from the audience. Uh, there is a question from Mankila. So how about if we mix with different fatty acid? What will happen?
Actually, I tried several fatty acid. So, for example, I use dodecanonic acid. Doesn't work with the molar ratio that I use. So we can try with, but maybe molar ratio to get the we can try to use, but we need to experiment with the molar ratio.
Okay, thank you very much for the answer. We have one more question from Dr. Muhammad Monirul Zaman. The question is menthol and DES, and are they produce solution or they just a physical mixture?
From what I understand, it is DES because the DSC result show that way, but it's from my understanding.
Okay, thank you. Let's see if we have more questions. I think yours is quite interesting topic and many questions from the audience. Okay, I think that's all. We have 3 questions for you. Thank you very much, No Azri, for the very good presentation.
Thank you.
Okay, next our presenter is Nur Erni Fatriah Kari from UTP. So her presentation title is Metal Organic Frameworks Screening MOF 74 Base for Carbon Dioxide Absorptions. Without further ado, let's welcome Noelni Fatria Kari.
Assalamualaikum and a very good day. My name is Nur Edwin Fatria Kari and I am from University Technology Petronas. I will present my research paper entitled Metal Organic Frameworks in Screening MMF74 Base for Carbon Dioxide Absorption. The co-author of this research paper are Dr. Azmi Bustam and also Ms. Marhaina Ismail. The outline of my presentation will be introduction, methodology, result and discussion, conclusion, and lastly will be references. This is the introduction of this presentation. The fossil fuel are the main energy used for energy supply. The massive in development of the industry will cause high demand of the fossil fuel. Fossil fuel emit carbon dioxide to the atmosphere, and in 2014, it is reported over 24% of the carbon dioxide emission are from fossil fuel, and over 81% of the greenhouse gas emission are carbon dioxide. If this can't control, it will cause climate change and also global warming. Intergovernmental Panel of Climate Change (IPCC) reported over 50% of the carbon dioxide concentration in the atmosphere needed to be reduced by 2050 in order to prevent the increasing of the temperature up to 2 to 2.5 degrees Celsius. And there are various technologies have been invented to prevent the emission of the carbon dioxide. First of all, membrane, cryogenic distillation, adsorption, and also absorption. So adsorption will be used in this study because it has low cost, low operational cost, and also high adsorption capacity of carbon dioxide. What is adsorption? Adsorption is the process of solid that holds molecule of a gas or liquid as a thin film. Adsorption has its adsorbent. Adsorbent must be robust in the presence of water, can be synthesized largely, and selectively adsorb CO2. There are various adsorbents commercially used, which is zeolite, activated carbon, and also alumina. And recently, researchers found that metal organic framework can absorb carbon dioxide up to 6 millimole per gram. What is metal organic framework? Metal organic framework is a crystalline metal coordination of bonds, metal ion, and also organic linkers. Different metal ion and also the organic linkers will give different function that can be used as the gas storage, gas separation, gas adsorption, and also as catalyst. And it is reported that MOF74 can perform high robustness in the presence of water that achieve the criteria of the adsorbent. Move to the next. There are various types of MOF, which is MOF74, zeolite 13X, MIL101, MOF5, and also CuPTC. It is reported MOF74 gives the highest adsorption capacity of CO2 compared with the other MOF due to the presence of the open metal site that favor to the CO2 binding mode. And MOF74 have high robustness in the water for nickel and also cobalt. MOF74 consists of DOT linkers with transition metals such as zinc, manganese, nickel, and cobalt together with the magnesium. And the structure that connects to the DOT linkers can make a hexagonal channel with P3 symmetric form and R3 space group. Nickel MOF74 gives highest robustness in water, which is up to 85% compared with the other metal centers. So, this research focuses on the molecular simulation. Molecular simulation used to emphasize how modeling can aid the structure and to predict the novel structures with targeted chemical and also to understand the structural behavior. And this molecular simulation will be used the process of GCMC, Grand Canonical Monte Carlo simulation. And the research objective will be to evaluate the capacity of MOF74 in capturing carbon dioxide by using simulation tools. That MOF74 will be assessed based on CO2 at 298.15 Kelvin with pressure from 0 to 1 bar by using GCMC simulation. The strategy of this study will be used Grand Canonical Monte Carlo simulation. Grand Canonical Monte Carlo consists of insertion, deletion, translation, and also rotation of the random search in the predicted adsorption isotope. And the material study software will be used for this project work. And first of all, we will draw molecular structure, and then we optimize by using foresight optimization for the energy of the molecule. After energy optimization have been achieved, we perform adsorption of the carbon dioxide onto MOF74 by using sorption model in the material studio. And this is the example of the MOS74 before the optimization. And after we optimize, we obtain hexagonal channel of the MOS74, and then the cell increase to the supercell by 2 times 2 times 2 to provide more accurate result than the normal cell. Move on to the next. For the result and discussion, based on this screening of MOS74 metal center, we found that nickel MOS74 gives the highest absorption capacity compared with the other metal, and cobalt gives the lowest absorption capacity, which only 5.66 millimole per gram. And simulation capacity will be higher due to the ideal condition compared with the literature and also experimental value. In comparison with the literature, in our simulation, it is found that nickel gives the highest absorption capacity compared with the other metal center, and for the literature, magnesium gives the highest absorption capacity. Even though for the literature it gives the highest absorption capacity in magnesium, magnesium reported to rupture in the presence of the water, which does not comply the criteria of adsorption criteria, which needed to be robust in the presence of the water. And nickel metal center reported to give high robustness in water, which is 85%, compared with magnesium that only up to 18%. So, to identify the best candidates, which nickel MOF74 gives the best segregation, which up to 12.35 millimole per gram compared with the other metals. And in the future, the model of the simulation should be include polarization or orbital interaction, and using X-ray diffraction and also IR spectroscopy for the molecule can help to improve the trend of the model. As the conclusion, the simulation to screen MMOS74, which consists of the transition metal and also magnesium, have been completed for adsorption of the carbon dioxide, and the presence of open metal site favor to CO2 binding that give higher adsorption capacity. And nickel MOS74 give the best metal center and provide a promising structure stability with the presence of water as reported by the previous literature. And further study should be done onto the effect of attraction energy of the molecule, intermolecular energy, and also body wall force to support this selection. And this is the reference of this presentation. And that's all from me. Thank you. In a very
Okay, thank you, Ernie Fatria, for the presentations. So we have a couple of questions for you from the audience. Okay, number one, how does the presence of water moisture going to affect on CO2 absorption performance?
Uh, Thank you for the question. So the presence of water, since water contain of H2O, so it will affect the binding towards the MOF74. So if presence of water H plus, presence of H plus inside of the water will bind directly to the MOF74 since it has stronger binding than CO2. So that's why the presence of water presence of water moisture will affect the CO2 absorption, and then it will reduce the absorption of CO2.
Okay, thank you for the answer. We have one more question. So the question is, what the uniqueness of MOF74 characteristic that that you choose that the best MOF type of for this particular application CO2 absorption? What the uniqueness of this particular MOF74?
For MOF74, why I choose MOF74? It has metal center for open metal site inside MOF74 itself. So the presence it's for CO2 absorption. So the presence of the open metal sites will increase the binding of the CO2. So that's why I choose MOS 74 compared with the other method. That is the first one, the units of MOS 74, and also metal MOS 74 have different metal, so it has robustness in the presence of the water.
Okay, thank you, Nu'ani Fatria. So I think that's all the questions from the audience. Thank you very much for both presentation and Q&A sessions. So
Thank
next,
you also.
yeah, so next we're going to have a presenter from Sojo University, Professor Katsuki Kusakabe. So his presentation title today is Co-carbonization of wood chips and polyvinyl chloride in glycerol. Without further ado, let's welcome Professor Katsuki Kusakabe to deliver his speech.
Okay. Thank you for the introduction. I'm Katsuki Kusakabe at Sojo University, Japan. It's a great pleasure to participate in the ESTCON Congress. So today, I'm going to talk about co-hydrothermal carbonization of polyvinyl chloride waste and wood chip for dechlorination. First of all, I would like to talk to you the background of this research. In Japan, a huge amount of PVC is produced every year. For example, various tubing pipe, PVC film for greenhouse, electrical wire cord, and so on. Waste plastics were generally treated by incineration and landfill. However, the thermal recycling of PVC is difficult and inefficient in Japan because it produces harmful hydrogen chloride and toxic dioxins. Landfill treatment has some problems such as the leaching of harmful chemicals. In addition, the space of landfill is limited in Japan. Therefore, research on efficient dechlorination method is required. In this presentation, we propose a hydrothermal co-carbonization process of PVC and biomass. Co-hydrothermal carbonization can promote synergistic interaction between two feedstocks by simultaneous hydrothermal carbonization. Biomass has a large amount of free OH groups. This OH group helps the conversion from organic chlorine in PVC to the inorganic chlorine. As a result, carbonization of biomass also progresses by the elimination of OH group. Objectives of this research are as follows. Co-hydrothermal carbonization of polyvinyl chloride film and wood chip was conducted at 200 to 260 degrees C in an autoclave filled with air or nitrogen for the chemical recycling waste by dechlorination of PVC. The effects of carbonization temperature and air oxidation reaction during co-hydrothermal carbonization on the decomposition behaviors of PVC and wood chips were investigated. This slide indicates the experimental procedures. Wood chips was milled into small pieces and dried at 105 degrees C in an oven for 2 hours. A commercially available PVC resin film with a thickness of 0.1 mm was cut into small pieces of several millimeters in size for use. 0.2 gram of wood chip, 0.2 gram of PVC, and 15 milliliters of distilled water were loaded into an autoclave reactor. The reactor was heated at 200, 220, 240, and 260 degrees C for 120 minutes. Separation of the hydrochat and liquid filtrate was conducted by vacuum filtration. The hydrochat samples were dried in a vacuum oven at 105 degrees C for 1 day. We measured the mass of biochar and chlorine content in PVC and then calculated the value of percentage decomposition and dechlorination yield. After the carbonization, we can separate the carbonized biomass and PVC. Therefore, the dechlorination yield was obtained from the chlorine content in carbonized PVC. This slide showed you the surface morphologies of the initial wood chip and hydrochar. You can see the elongated fibrous shape in the initial wood chip. When pyrolyzed at 200 degrees C, still the fibrous shape was remained and the disruption of the cell wall was small. Pyrolysis at 240 and 260 degrees C, the surface morphologies was greatly changed. The development of pore structure was notable due to the evolution of carbon dioxide and steam. As shown in figure at the right side hand, differential thermogrammetric analysis data supports the change of SEM image. Next, the percentage decomposition in air and nitrogen were compared to clarify the effect of oxidation on hydrothermal carbonization. Oxidation accelerated the decomposition during the hydrothermal carbonization of PVC. However, for the hydrothermal carbonization of wood chip and co-hydrothermal carbonization, a high percentage decomposition was obtained in a nitrogen atmosphere. Despite the low decomposition of PVC, the percentage decomposition of the PVC wood chip mixture was close to that of wood chip. A synergistic effect on the decomposition was observed at low temperature. We have summarized the result of the hydrothermal carbonization in this table. The synergistic effect on decomposition is observed only at 220 degrees C and a nitrogen atmosphere. On the other hand, in air, the value of the synergistic effect became less than 1 at all temperatures due to the increase in oxygen-containing functional groups. Conversely, the hydrogen char yield was high in air. This is a result of dechlorination of PVC. The dechlorination yield for the recovered PVC sample in nitrogen are higher than those in air. Even at the carbonization temperature of 260 degrees C, the dechlorination yield was approximately 40%. The main conclusion we have reached are the percentage decomposition in air was slightly lower than that in nitrogen. This indicates that oxygen-containing groups are formed on the surface of wood chip in an air atmosphere. Judging from the differential thermogrammetric analysis of hydrochar, dechlorination progressed at a low temperature. Thank you for your attention.
終わり。最初なんとか編集すれば終わりだな。
あともです。ここもです。Let's see where we have questions. Prof. Prof. Katsuki is here. Okay. Uh, I think for some reason, Prof. Katsuki Kusakabe cannot make it for today session. So let's proceed with the next presenter, which is our final presenter for today's sessions. So her name is Anna Nagai from Sojo University, Japan. So her title for presentation today is Preparation of Coporphyrin Catalyst Encapsulated in cyclodextrin-based metal organic framework for coupling reactions. Without further ado, please welcome Anna Nagai from Sojo University, Japan.
Thank you for the introduction. I am Anna Nagai. I am currently affiliated with the Faculty of Engineering. It's a great pleasure to participate the ICPEAM conference. So today I am going to talk about preparation of cobalt porphyrin catalysts encapsulated in CDMO for coupling reaction. First, I will explain the background of this research. Organometallic catalysts have been used as homogeneous catalysts in the field of fine chemical and pharmaceutical industries. The traditional metals in organometallic catalysts are expensive and belong to the rare metal. Moreover, contamination by the trace metal in the reaction product can cause toxicity in pharmaceutical products and significantly impair the properties of high-performance products. Thus, the development of the supported organometallic catalyst has emerged as a promising solution to obtain the reusable catalyst. If the organometallic catalyst could be imbalmized in the porous materials with a ship in a bottle structure, the resulting heterogeneous catalyst would be reused several times without the metal leak. Cobalt porphyrin TCPP will thus be introduced into the hydrophilic nanopores of CDMOF. Cyclodextrin-based metal organic framework CDMOF is porous organic crystal. CDMOF is prepared by the complex formation of gamma cyclodextrin, gamma CD, and potassium hydroxide. CDMOF crystal consists of the body-centered cubic structure of the primary gamma CD6 unit. The interior cavity of gamma CD is hydrophobic, while the exterior side is hydrophilic. Therefore, the hydrophobic nanopore shown in the blue box can be created by a pair of gamma CD tree. These special cavities with the diameter of 1.7 nanometer are newly formed at the center of gamma CD6 unit by the crystallization and are connected to each other through the aperture of the gamma CD along the A, B, or C axis. These special cavities are hydrophilic due to the free primary 6OH groups in gamma CD. Next, we will explain the coupling reaction of cresol by aerobic oxidation using a cobalt porphyrin catalyst. If cobalt TCPP could be introduced into CDMOF, the resulting cobalt TCPP CDMOF would be expected as a heterogeneous catalyst for organic synthesis. As far as we know, no investigation on catalytic reaction by organometallic compounds immobilized on CDMOF has been reported. In this research, we encapsulated cobalt TCPP catalyst into CDMOF during the crystallization by vapor diffusion of methanol. We carried out the coupling reaction of creosol by using heterogeneous cobalt TCPP CDMOF catalyst. We investigated the effect of catalyst concentration and crystal size for cobalt TCPP CDMOF on the reactivity. This slide shows you the experimental procedures. For the synthesis of cobalt TCPP, TCPP and cobalt acetate tetrahydrate were dissolved in DMF. The mixture was heated for 5 hours under reflex condition. For the crystallization of cobalt TCPP CDMOF. Cobalt TCPP CDMOF was formed by vapor diffusion of methanol to the feedstock solution, including cobalt TCPP. Oxidative coupling of creosol was carried out by using homogeneous cobalt TCPP or heterogeneous cobalt TCPP CDMOF catalyst in methanol. Creosol and base sodium hydroxide or sodium carbonate were added to flask with reflex condenser. The resulting mixture was stirred at 60 degrees C in oxygen. After prescribed period, the concentrations of creosol and biphenyl compounds were measured with HPLC. This part is the result of crystallization of CDMOF. As shown in this SEM image, cubic cobalt TCPP CDMOF crystal was obtained. The crystal size was 5 to 20 micrometer. When the crystallization conditions were changed, the crystal grew up to 150 micrometer. From the result of XRD, the crystal structure was found to be maintained when cobalt TCPP was introduced. The BT-specific surface area of the synthesized CDMOF is 970 square meters per gram, whereas the cobalt TCPP CDMOF has a BT-specific surface area of 682 square meters per gram. Here is the result of the creosol coupling. We prepared two types of cobalt TCPP CDMOF with the cobalt TCPP gamma CD6 molar ratio of 0.49 and 0.997. The pink plot shown in the figure is the result of homogeneous cobalt TCPP catalyst. The reaction rate of the heterogeneous cobalt TCPP CDMOF catalyst was slightly reduced compared to the reaction rate of homogeneous catalyst, because the diffusion resistance of creosol and the biphenyl compound in a CDMOF crystal was influenced. The reaction rate and conversion of two types of cobalt TCPP CDMOF catalysts were almost the same at the same cobalt TCPP concentration. The upper figures the effect of catalyst concentration, and the lower figure shows the effect of catalyst size. The following results were obtained regarding the catalyst concentration. The reaction rate was much higher at high catalyst concentration. The initial reaction rate was approximately proportional to the catalyst concentration. Next, regarding the catalyst size. The conversion of the cobalt TCPP CDMOF catalyst with a particle size of 100 to 200 micrometer was significantly lower than that of a cobalt TCPP CDMOF catalyst with a particle size of 5 to 20 micrometer. This result indicated that the intergranular diffusion resistance of creosol or biphenyl compound was found to affect the appearance reaction rate. We summarized our conclusion as follows. Cobalt TCPP could be introduced into the hydrophilic nanopore of CDMOF crystal by the co-crystallization method. The catalyst loading of cobalt TCPP in CDMOF reached to 9.88%. When CDMOF was used as the support material for the organometallic catalyst, a heterogeneous catalyst having both high dispersibility and high loading could be achieved. In order to evaluate the catalytic activity of the cobalt TCPP CDMOF, the oxidative coupling of creosol was performed. For the heterogeneous cobalt TCPP CDMOF, almost the same performance as the homogeneous cobalt TCPP catalyst was obtained. When cobalt TCPP CDMOF crystals with a particle size of 100 to 200 micrometer were used, the reaction rate was found to decrease due to the influence of interparticle diffusion resistance. Thank you.
Okay, thank you, the presenter, Ms. Anna Nagai from Sojo University of Japan. So we are towards the end of our session today. We're having very great presentations from 7 presenters. I would like to thank you very much to all the presenters for the great knowledge sharing and the information, as well as the audience that give a lot of questions and interest throughout the session. With that notes, I end our session today, and don't forget to have we have open ceremony in the afternoon sessions around 2 p.m. Everyone is welcome. Okay, with that, thank you very much. Bye.